here's a problem. Show that there exists a countable set S and an uncountable family F of subsets of S, such that for any A, B, and F, the set A intersection B is finite. Try it out for yourself. We've already given one solution in a previous Instagram post, and today we will be providing another solution. Consider the first quadrant of the Cartesian plane and divide it into a grid of unit squares. For an explicit representation of the squares, we may for example represent each one of them by the coordinates of its bottom left vertex. For example, this square right here is represented by 1, 2. Then, the set of all of these squares is represented by n cross n, which is a countable set. For example, you can check that the following mapping from n cross n to n is injective. So this set will serve as the countable set S in our problem. To determine the suitable family of subsets of S, consider a line that makes a certain angle theta with the x-axis, where theta belongs to the interval 0 pi over 2, and take a subset A theta of S consisting of the squares that the line intersects. If we take two different angles, theta 1 and theta 2, then as we move away from the origin, the corresponding lines grow further apart from each other at a linear rate. In particular, no matter how close the two angles, there always exists a certain radius from the origin, beyond which, any time we take a point from one line and a point from the other, they will have a distance larger than square root of 2. Notice, on the other hand, that any 2 points on a unit square have a distance no larger than square root of 2. So this implies that the two subsets A theta 1 and A theta 2 have no elements in common after this point, since it's impossible for one square to be intersected by both lines again. In other words, A theta 1 intersection A theta 2 is finite. Thus, taking the family F as the set of all of these subsets A theta, since the interval 0 pi over 2 is uncountable, we find that all conditions are satisfied and we are done.